Welcome to module 39 of object oriented analysis and design. Over the several modules, past modules, we have discussed at length about UML diagrams, and we have discussed about variety of structural as well as behavioral diagrams. Now, in this module we will quickly familiarize with you with a number of other UML diagrams which are still left out. We do not have enough time to really go through each one of them at length. So, I would just briefly familiarize you and leave it to you to read about them later, and this will complete the discussion on UML diagrams. So, the 5 diagrams that we would like to talk of, one belongs to the behavioral type and 4 belong to the structural type, which will form the outline of this discussion. So, just to remind you, the structural diagrams of UML show the static structure of the system and parts of different abstractions at a level, and the behavioral diagrams show the dynamic behavior, basically showing you how does the system behave over time. So, these diagrams also in a varied way does that. So, if you look into the overall diagram classification of UML 2.5, the standard that we have been discussing, these are the diagrams we have done. Object almost not separately, but then almost we have done. There it is not pretty much in use anyway. We have talked about use case diagrams, activity diagrams, sequence diagram, communication diagram, interaction overview diagram. So, these are the major diagrams, the state machine diagram. So, we have discussed about all the major diagrams, particularly the diagrams that are significantly involved in the analysis and design phase, and that is where our focus is, because we are talking about object oriented analysis and design. But there are few diagrams still left out, certainly the timing diagram here in the behavioral part, and the package diagram, composite structure diagram, component diagram and deployment diagram. These are diagrams which also come in handy, but may have a less connection in terms of the object oriented analysis and design. So, these are just for your knowledge in terms of completion of the understanding of UML, but these are diagrams which appear more during the implementation phase, when you are actually organizing the code, putting components in the architecture and so on. So, they are very necessary for the system, but beyond the basic concept of encapsulation and interface, they may not add real further value in terms of the object oriented modeling. So, we will quickly go through these diagrams one after the other. The timing diagram, as I said, is a behavioral diagram, and actually the timing diagram is again like you saw in the state machine diagram. You saw a state machine diagram is a generalization of the finite state machine models that we use in automata and switching theory and different other places. So, timing diagrams are also generalizations of the typical timing displays that you have seen for different hardware description. The only difference is that the time diagrams here are not necessarily meant only for the hardware systems or only for the electronic systems, they are also meant for different software descriptions. They primarily arise in the analysis phase and that get refined in the design phase, and these are the major components. Naturally, you can understand that since we are talking about time, lifeline would be a major part of this diagram. Then you have different kinds of duration and time constraints and so on. So, let me just take an example and quickly walk you through that. So, this is this is a very simple scenario being shown here, which is in terms of trying to access a particular URL. So, you can see that there is a web user, there is a web browser, there is a DNS resolver, and there is a web server. And this happens in 4 different swim lanes. These are the concurrent timelines. So, this is the lifeline, this is a lifeline, these are all different lifelines. So, these are all concurrent lifelines happening. So, each one will go on having its own timing diagram, and they will interact between themselves. So, for example, if you start here, the web user. So, as if I am sitting in front of a my browser and trying to access a URL. So, initially I am in idle and then I request for a URL. So, as I request for a URL, a synchronous message, this is a synchronous message sent to the web browser, and which was, so these are the different states of the particular lifeline. So, this was in idle state, and as soon as I send a synchronous message, is a synchronous message in the sense that once I send this, I will be in a hold state. So, I am in a waiting state, I cannot proceed. That is what we all know, that if we have requested for a URL, we have to wait for that URL to actually come. So, this synchronous message then makes a state change from idle to processing, as you see here, and then it sends. So, it does certain computation and sends another synchronous message to the DNS server to resolve the IP address. So, my original request was to www.google.co.in. Now, I have to get the IP address for that. So, that IP address will be requested here. So, DNS server which was in idle will now change to processing, it makes a state change, and this is a duration constraint which specifies as to how much time will it take to actually find out the IP address given the URL of the page that I am looking for. So, once it has found that out, so let us be clear. So, once it has found that out, it again reverts back to the idle state from the processing state, and corresponding to this synchronous message, it sends the response back. So, here in the web browser, I know I was waiting for that, and I change my state, the web browser changes its state and goes into the processing stage. So, now it has got the IP, now it has to actually go and get the page. So, who will get the page? The web server will get the page. So, it now sends a request to the web server which was waiting, and as soon as it gets this synchronous message, changes state and comes into the processing. So, it is trying to find out where to locate that page in the whole internet, and then it does that, and when it is ready to have found out the page, that it will send the response, which is the reply message, which not only responding, but it will also actually send that page back. And there is a duration constraint here, which say that if it cannot respond to this message within this time, then beyond this time it will possibly actually get back with a cannot respond kind of feature. So, the page could not be found kind of. So, once the reply has come back to the web browser, then the web browser will show this page, and this is the again the duration constraint to show the page. And when it is showing the page, it sends back the response corresponding to this message, and I was waiting for the page to come, I was on a hold, I was on a blocking call, and now I get the page. So, I again change my state and get into viewing. So, this is you can see that a timing diagram can very nicely show not only the sequence of activities that are happening, which you would have seen, which you will see equivalently in the sequence diagram as well, the corresponding sequence diagram, but here it actually shows you in terms of the time period in terms of which these things will have to happen, and in terms of the time lifeline of each as to in exact clock time when what is expected and how much delay is expected and so on, what is the time bound of certain things to happen. So, you have the timing diagram is very critical for the behavior of, you can certainly make out that if you have a completely offline system, you will not have any significant timing diagram for that, but timing diagram is significant for any real time system, where there is an expectation of messages being responded to or certain events being reacted on based on a fixed time boundary. There is a fixed time target within which the tasks will have to be achieved, or the events will have to be responded, and for that certainly you need to express that, because sequence diagram, as we said, if you can recall, we said that sequence diagram just gives you the sequence. It may not necessarily tell you the time lapse between one message to the other, or between one message to his response and so on, whereas the timing diagram very frequently you would like to say that and also keep track of the internal states of the different lifelines, so that the signal timing can be managed. So, this is the last of the behavioral diagrams that we wanted to discuss, and now I will move on to quickly take a look into the remaining structural diagram. So, first is a component diagram, which is a structure diagram. Let me go back to the red pen. So, this is the structure diagram, which shows, as the name suggests, it shows the component diagrams. So, it will primarily occur in the design and implementation phase, because till you come to design, there is no question of identifying components. And so, you identify components in the design phase, and in the implementation phase really either you acquire components or you create components and then you connect them together. So, component diagrams have a major use in terms of component based development. This is a certain style of development which is very widely used, where you try to write very little amount of code yourself, but you try to identify different components from different third party sources, and which satisfy the requirements of different subsystems that your system has or system may be designed for, and based on that you connect these components, or maybe you write some proxy wrappers around these components to achieve the actual functionality. And I am sure many of you are familiar with SOA, which is service oriented architecture, where basically instead of actually just looking into function calls or object invocation, you can actually request for certain bundle of services to be provided, and this is becoming very common these days, with very common infrastructure getting into the cloud and so on. So, whenever you have this kind of a scenario, the component diagram could be really useful. It is important to understand that what is the basic notion of a component. A component may be logical or it may be physical. It may be logical in the sense that I am saying that this is a business component, but that does not necessarily mean that this is a physical hardware, or there is a single library or a collection of library which is a business component. A business component could have a logical boundary simply, that this is where the business is transacted, this is where the process is transacted, the process component. Or it could be physical components, like these are the different I have listed primarily the software based components. You could think of this as actually hardware components also in many places. For example, if you go to the domain of automobile, you will often find that you need a whole amount of component based development, but in therein all physical components may not just be software blocks, they could also be hardware blocks, embedded systems that come in and so on. So, there are different components of a component diagram. So, I would just do a small illustration with an annotated diagram. These annotated diagrams are really useful for you to understand this better. So, we are talking about if you look into, certainly by now you understand the style of UML. So, this is one component, this is another component, and this is another component, and these are kind of little big components. So, you say by the keyword subsystem components. So, these are subsystems that you are building up, and this in turn we has this subsystem component of web store, which is to use certain web searching activity, has three different subcomponents in that: the search engine to search, the shopping cart for online shopping, and the authentication for maintaining user sessions. Similarly, the warehouse, where you actually have the inventory, has an inventory subcomponent, the accounting has order as well as customer to take care of. So, these are the basic component structure. You can see that there is an implicit hierarchy of containment in terms of the components, and components really connect and talk to each other through what is known as ports. So, basically how do you connect? You have different ports, and ports are to have the required interface, because you cannot for example, you cannot just I mean, if you think of it this way, that if you have a 3-pin male plug, you cannot insert that into a 2-pin female connector. So, these are ports and they need to have the same interface. So, for a 3-pin plug you need a 3-pin connection. So, in a similar manner you need the required interface to be supported on these ports, and through that you can connect the components as you can see here. As you can see here, the detailed notation you can read up when you actually need, and then you can provide a separate interface, external interface also of online shopping, of user session, of product search, or you can, or ports could just be internal to the system, like this is a connection from one subcomponent to another subcomponent within the web store component, which is internal connection that you have. So, whenever you have this requirement, you put some kind of special connectors which are called assembly connector, ball and socket connector. So, just to keep similarity with the connectors in the physical world. So, in this way the component diagram gives you a good idea in terms of the different software components, where how they are contained hierarchically and who connects to which port of which component through what interface and so on. And there are connectors can be, so you have ports, you have connectors, you have those connectors can be delegated, that is specialized and connected for building up the whole system. The next kind of diagram that you will see are again structural diagrams, but these are structural diagrams for deployment. A deployment basically is in terms of the architecture of the system. So, the overall, so far we have been just talking about software as soft. So, this is a collection of code, a library, binary and so on, and you just put them all together and you say this is my component, this is my software, this is my activity and so on. But finally, it has to get to certain in terms of certain physical sense, which we say are artifacts. Artifacts are like the final physical realization of the different parts of the software, the executable files, the libraries, the archives, the actual database and so on and so forth. And you will have targets or devices on which these archives work. So, you will have servers, you will have different mobile devices on which. So, the deployment diagram will tell you which artifact is to be located in what target. So, that is the main purpose of the deployment diagram, because had it been earlier we used to have a single system which had everything. So, the deployment was really not an issue, but now any system small or large will have different target systems, different processor boards, different motherboards, cores, different servers themselves, different cluster of servers themselves and so on. So, even if you have a software component information, you need to decide what piece of your system works on which target and how do they communicate between them. So, deployment diagram will basically tell you how you organize all those into the final system architecture. So, this is just showing you another annotated simple example. So, these are your artifacts. So, this is a web.xml. So, this is again a kind of web access online shopping example. So, this is a file, the XML file which kind of configures the system. This is a jar file. Those of you who know Java would identify a jar file. If you do not identify, it is fine. You can just assume that this is a library which kind of provides the shopping cart functionality. This is another Java library which provides the orders functionality and so on. So, these are the different artifacts that you have, and you can see that how these are physically deployed. So, this is physically deployed in terms of a folder. You can see this is a folder lib in which you have these artifacts. So, this is the container, this is the target in which you have these. You have another folder web inf which contains this folder lib as well as it contains this artifact. So, looked from this folder's point of view, this lib folder turns out to be an artifact, and then you can show that where does this particular artifact manifest. This is called the manifestation, which will basically relate it to the component which uses or which is realized in terms of this library. This library is a physical entity, is a physical binary code, jar code of the functionality, and this is the dynamic component which has the behavior when it executes. So, this basically is a logical component that you have, which will. So, the jar code, the physical binary code, when executed will manifest itself in terms of the component behavior. So, that is the basic purpose of the deployment diagram, and these are some of the other examples of deployment, which is this is called a specification level deployment. You may not follow every details here, but just try to understand. Here we are actually talking of devices. This device is Sunfire X4150 server. So, this is actually a physical server you are talking of, and then within that you have another which is called the execution environment. This execution environment, that is a Tomcat. Tomcat is nothing but a web server which is regularly used, and then you have another execution environment which is Catalina servlet container. Now, this is something of a execution environment that the user has created through certain other third party support. So, these artifacts that we just saw, they now get deployed in this execution environment or in this device. That device itself is deployed in the server. So, it works in terms of that, it works on that server. Similarly, there could be another device which is another server which communicates through certain TCP/IP protocol, and these are different inventory, orders, users. These are different artifacts which are deployed in here using an execution environment which is Oracle database 10G. So, all this information, as you can see, was not available while we talked about the other diagrams, but here we are specifically trying to look into these and get the details of system specification level deployment. This is just another variant of this. This is called the instance level deployment. So, earlier we just talked about this particular server, which is a generic class. So, there will be hundreds of such servers available in the world, and here you talk about just the specific instance of that server. So, this is you get to this level when you are ready with your system, or you are about to be ready with your system, and you really want to know what are the servers on which you will put these different components, different artifacts to actually execute. So, that is why this is called the instance level diagram. You now have the instances of these. You have an unnamed instance of Tomcat which is actually running here and so on. So, that is the job of the deployment diagram. The next is a composite structure diagram. The composite structure diagram is again basically a structure diagram which show you the internal structure diagram and a collaboration use diagram. So, it shows the internal structure of a classifier. Classifier is kind of a system which can be decomposed into its properties and parts, and we can also show collaboration. Let us quickly go to an example. So, here we are talking about a bank ATM, and this is we are trying to show the internal structure. So, in terms of the internal structure, now you can see that what does you are trying to describe now the internal structure of an automatic teller machine. So, it must have a display, obviously, it must have a card reader where you put the card, it must have a keyboard pin pad so that you can key in the print, it must have a processor, it will have a modem to connect to through the well link, it must have an encryption processor, crypto processor, it must have memory, and certainly it must have a vault. The money has to reside somewhere. So, all these are significantly are not really all software components, they are physical components, the hardware components. So, the internal structure diagram, the internal structure is showing that this is how the different parts of the system, the composite structure, that is the reason this diagram is called a composite structure diagram. So, some of these might turn out to be, for example, whatever you put in here in the crypto processor could be a software component, but you need to understand the physical structure, physical internal structure of the system to be able to realize really how different how the whole system will get into being. And interestingly, like you have a printer as an internal structure, and you can see how you show that with a dotted line, because it is a reference role, in the sense that we are saying that bank ATM, the reference role means that the bank ATM will have a printer, but that is not a part of the ATM machine, but you will have a printer. So, the printer is will be put in by somebody else, and which the bank ATM would be able to use. Besides that, there are different collaboration use. I will skip these, you can study them. These are some of the other ways you can show the composite structure, and I will rather move on to the package diagram, which is another very important diagram. The package diagram, so far mostly if you see in terms of the component, in terms of the internal structure and all that, we were primarily trying to take the whole system and trying to break it down into different parts. In the package diagram, we try to do the reverse. What we try to say that we have different components, we have different parts. How should we put them together into different envelopes, into different packages, so that they can be better managed, they can be better maintained. So, packages again have a number of components through which the package diagrams express themselves. So, this is again looking into an example. So, here you are saying that there are different packages like web shopping package, the mobile shopping package, the phone shopping package, and the mall shopping package. So, these packages basically contain all that you need to do in terms of the shopping on the web, all that you need to do in terms of shopping through your mobile phone and so on. And then you could as these dotted blue lines show, then you can merge them together. This is called a package merge, and make a bigger package. And then you say that my shopping cart component actually is having this package to use. So, this packaging really helps you to refer to a multiple independent parts in terms of a common generalization, and these are the individual packages, and then you could define dependencies between the different packages. This is a payment package and this is a web shopping package. So, you can say that they have a dependency in terms of a use of the payment using the web shopping and so on. So, these are the different package diagrams. So, to summarize, we are trying to conclude on the UML diagrams. So, we have already done the different structural and behavioral diagram discussions. In this module, we tried to talk about one more behavioral diagram as timing diagram and 4 other structural diagrams, and this will complete our exposure to the UML diagrams as a whole, and we are now equipped to use the whole of UML to model and represent and refine any situation of analysis and design, and in some cases might take them to the different stages of implementation as well.